Chapter 10, Event-Driven Applications and Functions. This chapter covers understanding event-driven architectures, using RabbitMQ as a message broker, implementing functions with Spring Cloud Function, processing events with Spring Cloud Stream, producing and consuming events with Spring Cloud Stream. In the previous chapters, we worked on a system of distributed applications that interact according to the request-response pattern, a type of synchronous communication. You saw how to design the interaction both in an imperative and a reactive way. In the first case, processing threads would block, waiting for a response from an I/O operation. In the second case, threads would not wait. A response would be processed by any available thread asynchronously once it was received. Even if the reactive programming paradigm lets you subscribe to producers and process the incoming data asynchronously, the interaction between the two applications is synchronous. The first application, the client, sends a request to the second one, the server, and expects a response to arrive in a short time. How the client processes the response, imperative or reactive, is an implementation detail that doesn't affect the interaction itself. No matter what, a response is expected to arrive. Cloud-native applications should be loosely coupled. The microservices expert Sam Newman identifies a few different types of coupling, including implementation, deployment, and temporal coupling. Let's consider the Polar Bookshop system we've been working on so far. We can change the implementation of any of the applications without having to change the others. For example, we can re-implement catalog service using the reactive paradigm without affecting order service. Using a service interface like a REST API, we hide the implementation details, improving loose coupling. All the applications can be deployed independently. They're not coupled, reducing risks and increasing agility. However, if you think about how the applications we built so far interact, you'll notice that they need other components of the system to be available. Order service needs catalog service to ensure that a user can order a book successfully. We know that failures happen all the time, so we adopted several strategies to ensure resilience even in the face of adversity, or at least ensuring a graceful degradation of functionality. That's a consequence of temporal coupling. Order service and catalog service need to be available at the same time to fulfill the system requirements. Event-driven architectures describe distributed systems that interact by producing and consuming events. The interaction is asynchronous, solving the problem of temporal coupling. This chapter will cover the basics of event-driven architectures and event brokers. You'll then learn how to implement business logic using the functional programming paradigm and Spring Cloud Function. Finally, you'll use Spring Cloud Stream to expose the functions as message channels via RabbitMQ, building event-driven applications through the publisher-subscriber pub-sub model. Note: the source code for the examples in this chapter is available in the Chapter 10/10 Begin, Chapter 10/10 Intermediate, and Chapter 10/10 End folders containing the initial, intermediate, and final state of the project. See this link. Section 10.1, Event-Driven Architectures. An event is an occurrence. It's something relevant that happened in a system, like a state change, and there can be many sources of events. This chapter will focus on applications, but events can very well be happening in IoT devices, sensors, or networks. When an event occurs, interested parties can be notified. Event notification is usually done through messages, which are data representations of events. In an event-driven architecture, we identify event producers and event consumers. A producer is a component that detects the event and sends a notification. A consumer is a component that is notified when a specific event occurs. Producers and consumers don't know each other and work independently. A producer sends an event notification by publishing a message to a channel operated by an event broker that's responsible for collecting and routing messages to consumers. A consumer is notified by the broker when an event occurs and can act upon it. Producers and consumers have minimal coupling when using a broker that takes the processing and distribution of events on itself. In particular, they are temporally decoupled because the interaction is asynchronous. Consumers can fetch and process messages at any time without affecting the producers whatsoever. In this section, you'll learn the fundamentals of event-driven models and how they can help build more resilient and loosely coupled applications in the cloud. Section 10.1.1, Understanding the Event-Driven Models. Event-driven architectures can be based on two main models. Publisher-subscriber, pub-sub. This model is based on subscriptions. Producers publish events that are sent to all subscribers to be consumed. Events cannot be replayed after being received, so new consumers joining will not be able to get the past events. Event streaming. In this model, events are written to a log. Producers publish events as they occur, and they are all stored in an ordered fashion. Consumers don't subscribe to them, but they can read from any part of the event stream. In this model, events can be replayed. Clients can join at any time and receive all the past events. In a basic scenario, consumers receive and process events as they arrive. For specific use cases like pattern matching, they can also process a series of events over a time window. In the event streaming model, consumers have the additional possibility of processing event streams. At the core of event-driven architectures are platforms that can process and route events. For example, RabbitMQ is a common choice to use with the pub-sub model. Apache Kafka is a powerful platform for event stream processing. The event streaming model is fascinating and growing in popularity, thanks to the many technologies developed in the last few years, allowing you to build real-time data pipelines. It's a complex model, though, that deserves its own book to be taught effectively. In this chapter, I will cover the pub-sub model. Before we analyze this model in more detail, I'll define some requirements for the Polar Bookshop system, and we'll use them as a means to explore event-driven architectures with the pub-sub model. Section 10.1.2, Using the pub-sub model. In the Polar Bookshop system, we need to implement an event-driven solution to allow different applications to communicate with each other asynchronously while reducing their coupling. These are the requirements. When an order is accepted, order service should notify interested consumers of the event. Dispatcher service should execute some logic to dispatch the order. When an order is dispatched, dispatcher service should notify consumers interested in such an event. Order service should update the order status in the database. If you paid attention, you probably noticed that the requirements don't specify which applications order service should notify upon order creation. In our example, only the new dispatcher service application will be interested in those events. Still, more applications might subscribe to the order creation events in the future. The beauty of this design is that you can evolve a software system and add more applications without affecting the existing ones at all. For example, you could add a mail service that sends an email to users whenever an order they made has been accepted, and order service wouldn't even be aware of it. This type of interaction should be asynchronous and can be modeled with the pub/sub model. Figure 10.1 illustrates the interaction and describes three flows for accepting, dispatching, and updating an order. They are temporally decoupled and executed asynchronously. You will probably notice that the operations for persisting data into a database and for producing events have the same numbered step. That's because they belong to the same unit of work, a transaction, as I'll explain later in the chapter.
Figure 10.1. Order service and dispatcher service communicate asynchronously and indirectly by producing and consuming events that are collected and distributed by an event broker, RabbitMQ.
In the rest of the chapter, you'll learn a few technologies and patterns you can use to implement this event-driven design for Polar Bookshop. RabbitMQ will be the event processing platform responsible for collecting, routing, and distributing messages to consumers. Figure 10.2 highlights the event-driven part of the Polar Bookshop system after we introduce the dispatcher service application and RabbitMQ.
Figure 10.2. In the Polar Bookshop system, order service and dispatcher service communicate asynchronously based on events distributed by RabbitMQ.
The following section will introduce the basic concepts of RabbitMQ, its protocol, and how to run it in your local environment.